Okay. Hello, everyone. I think we are day 6. We're halfway. And this is probably the most theoretical part, although we're not going to see equations here. Again, I like the term information capacity because it has to do with the question that everyone has or had for many years, like how much data can my model fit? And, that goes back to even Kolmogorov complexity when you have, it was going the other way around. They have a set of data, what's the smallest program that can reproduce that data? I think this is a bit of the inverse. I have the model, how much training data can I represent with that, and what can I do? I mean, we're not going to get a definite answer, but we're going to see some things around that, and a specific keynote in the workshop that I had never heard that group before. I didn't know those theories. There's a lot of references, and when I find time, I want to dig into that more. But if I found it extremely useful. So let's not keep the agony here. So the first thing that I wanted to start with is with the test of time award. I haven't spoken much about the test of time. We're going to see the test of time in the vision part, because half of it, one paper was the GANs, was in vision. The other was in sequence-to-sequence modeling. And because it was covered very extensively in the media, I haven't put much over here. But this slide is from Ilya Suskivert and Kwok Lee paper. It was the LSTM paper, sequence-to-sequence learning with neural networks, the precursor of the transformer. And here they had a slide that says what we got right. The deep learning hypothesis is that human perception is fast. Neurons fire at most 100 times a second. Humans solve perception in 0.1 seconds. Our neurons fires 10 times at most. Anything a human can do in 0.1 seconds, a big 10-layer neural network can do too. So that's kind of like a lesson that we've learned. But so I present that just to kind of connect that there is some rule of thumb between human cognitive tasks and deep learning tasks. So that's kind of like the analogy in the capacity and the translation into time, cognitive time, and neural network architecture. So this was an interesting paper, and I realized something else had been in the news even before that. But that's an interesting phenomenon. It says pre-trained large language models use Fourier features to compute additions. And I have to say that wasn't even an oral paper, but while I was going through the slides, I believe I was with Agapi, I don't remember, it caught my attention and I started reading more about it. I asked the author. So here are some interesting statistics. So there's unusual error patterns in language model addition performance. So, in the open source problem, the GPT-J, 93 errors are multiples of 10. 73% of the errors are also multiples of 10. And the closed source models, the zero shot, 100% of the errors are multipliers of 10. And the Palm, that's GPT-4, and in Palm 2, 87% of the errors are multiples of 10. So the takeaway here is that LLMs perform addition in unexpected ways, not simply remembering answers. So that's interesting. And people analyze the logic patterns, and they found that actually, so this is the logic lens, but yes, this is a logic across layers. So this is the logic across layers, not the logic that you see in the output. And they realized that some layers are predicting the parity of the answer. So they start seeing some you can see that there's some periodicity over here. And once you see periodicity, the next things that come into your mind is like, well, let's do a Fourier transform. And they did Fourier transform, and here you see you see some weird frequency spikes. I don't know if that 10 has to do with the multiple of 10 that the authors were talking about, but that was really weird. And they put a little bit more signal processing. They cleaned up the signals a little bit. And so this is a cross layer index, and this is the magnitude. So this looks like a two-dimensional Fourier transform here, or the window Fourier transform, to be more accurate. And they started seeing some interesting, spikes. For example, the fact that it's very sparse. It's also very interesting. That makes it even more periodic. And the question is, where do these periodicities come from? And they actually did an experiment and say, when we train from scratch on addition, so all these pre-trained models were not trained on addition. The the Fourier periodicity, the periodicity goes away. No more features, Fourier features are found. I don't know yet how to interpret that, but I think it's very interesting. At least we know that if we pre-train it, we basically we can make it work better in addition. And here's an interesting observation, because Fourier features are learned in the number embedding during pre-training. So, whenever you have specific tokens that they have to numbers, they kind of elicit some type of Fourier periodicity. And you can see here that you look at the pre-trained GPT-2 XL and the fine-tuned GPT-2 XL, and you find the same pattern. So no matter how you fine-tune the model, the periodicity patterns don't go away. And I think you see that also in Roberta as well, and Pi too. And basically this says, with solely the pre-trained number embeddings, GPT small is able to learn addition with 100% accuracy. So basically, if I remember correctly, this experiment is the following: you take GPT-2 and you fine-tune it to learn addition, and you can teach it addition if you use the pre-trained embeddings. But if you replace, if you try during fine-tuning to also learn the embeddings as well, then you don't perform as well. So if I had to take a takeaway, conclusion from this paper, it would be that somehow magically the pre-training with next token is helping you learn some interesting representation for numbers that you can further use them to teach it math, addition, which is not the case if you try to fine-tune and learn the embeddings at the same time, because probably you're overfitting over there and you're trying to parrot. So I think we're going to see more on that. The other thing which I find interesting, like you would assume that we solve the problem of tokenization, we have an architecture, people are happy. Does it really make any sense to go and revisit that part? I have to say, it always looked a little bit hackish, the way that and it does play a big role. How you tokenize, it can make a big difference in the language model. And it wasn't very rigorous, and it worked in the beginning. And once you find something working, people wanted to really take the slide of the scaling curve and make bigger and better models, but you know, it was always bothering them. So here you see different types of tokenizations, and that's what I was basically saying, that different tokenizations have different scaling curves. So here you have the byte level and the subword level, and you can see that the sentence piece is the one that it works the best. And the question is, we would like to avoid tokenization. Why? Because we want to have less modeling complexity. There's less adversarial vulnerability. I don't know that much in detail, but I'm sure I've seen it in adversarial attacks on language models. I don't know how it works. And better character level performance. So basically, people, they would like to really go at character level. And they would really, really want to take the, you know, I think we had with the window transformer, the byte level, as we call over here, to be as good as the sentence piece. And here's kind of like the trick. They have space is all you need. That's what they're trying to say here. And in fact, what they're trying to do is they're trying to do character level embedding, sorry, character level tokenization. And they realize that where you need most of the help, and look, so here, so what they're doing here, these are the transformer blocks, local global transformer blocks. Notice that you know, when you are in the middle of the word, they use transformer blocks that they are kind of like more lightweight, and when you are close to a space, they put the global ones are you know, heavy duty, because they realize that when you need most of the power of the transformer is during space where you are changing word. Okay, and this is kind of like an example, and they basically showing you where they are introducing larger transformer blocks. And it did the trick. Now space byte performs slightly better than the subword model, so that's kind of a success. And here's the conclusion. We introduced space byte, a multi-scale transformer architecture, model byte level language rather than tokens without performance penalty. Also, you know, the tokenization has the problem when you go from one language to the other, things become more complicated. Limitations, future work. You know, obviously there's still the problem languages that don't use space characters like Chinese. So you introduced other problems. You didn't solve Chinese, you solved all the other languages except for Chinese and similar ones. Batch inference is more complicated. Multi-scale modeling at larger scales still an issue. So, you know, people even think that you should go, you know, when you model a sentence level rather than word level, you know, what do you do there? Okay, so we're 15 minutes in, and this is kind of the last talk for today. That was an invited talk at the UniReps, Unifying Representations in Neural Models. I have to say that in most workshops, the titles were not very informative, and I kind of found that, you know, workshop because of that. There were other interesting talks as well, but I found this workshop because of this keynote invited talk title, which was really great, as you're gonna see. So it comes from the Flatiron Institute and Simon's Foundation. And the title is Computing with Neural Manifolds, Multi-Level Theory of Neural Representation in Biological and Artificial Neural Networks. I haven't found anything like that so far. Okay, so that was, where were these people all this time? So understanding the brain through the multi-scale theory of neural representation. So you might think it's kind of one of these theoretical ones about neuroscience. not really. It's actually a very practical talk. So, we know that there is some connection between statistical physics, machine learning, through the neural representations. Let's not all forget that Hinton studied from the deep belief networks and Boltzmann machines, that they were, statistical physics. This is the reason why they got the Nobel in physics. Okay, this is the connection. And we have all these connections, all these tasks, classification, estimation, prediction, motor control, decision making. And I don't know how many people in the audience are particularly familiar with the neural manifolds, but think about them as multi-dimensional shapes. Okay, and we're gonna see how this idea of manifolds is so fundamental for understanding, in fact, for even building neural networks. I want to make a small digression. If you go trace back, let's say, Benzio's research from the beginning, and you can see how he made the jump to neural networks, you will realize that the last area before that was manifold learning. It was this idea of finding strange geometrical shapes and kind of model or approximate them. And as this happened to be my PhD, manifold learning was my PhD, and I kind of stopped at the point where it took the neural network turn. But that was exactly the motivation. Everything started from this, the study of the manifolds. And let's see an example. So it says, for simple tasks as fine discrimination or estimation, approaches based on information theory and signal detection work really well. So this is about, trying to find out, a class A or class B, and you're trying to find out distributions of features that they're well separated. Okay. But, when it gets into more complicated stuff, you need to resort to geometry right here. So here's kind of like an interpretation of capacity. How many neural manifolds categories can you pack into the neural activity space while linearly decodable? Per neuron information content about object classes. So basically what this thing is telling you is that this geometric area represents to dogs, goes to dogs, and this geometric area represents to cats. Okay, and your volume or your area depends on the number of dimensions you are. And the question is there a way to, when I go to 100 dimensions, how many different cats and dogs can I fit, or how many categories can I fit? And basically here they tell you that when your representation, your geometry is not right, you can't fit that many. But when you untangle them in the same space, you can fit more. Okay. That goes back to something that people used to call dimensionality reduction, to try to find out how many true dimensions you have in your data set, so you realize the size of your model. And so the manifold dimensions, basically the dimension that the number of your parameters, and then in this geometry you're trying to characterize like the radius, like the size. You're trying to find some measurements on that. And then you also want to find, if you have a correlation of dogs and a manifold of dogs and a cat, are they, intermingled, tangled, or is there a way to separate them? And basically what neural networks layer by layer are trying to do is to start from a manifold that looks like that and taking it into a manifold that looks like this. Okay. And the talk is quite technical, and I'm not going to get into the details, but if there is something to understand here is that we kind of like have a formula now, or they start forming a formula. It says representation geometry formally predicts neural manifold capacity. So basically is if you make some measurements of your geometry of your data, you can predict how many dimensions you're going to need. So Again, I just wanted to give you a flavor. This deserves kind of like a more exploration, but I wanted to give you over here is kind of like the motivation that we have a theory of neural manifolds as a multi-level probe from neural population. Okay, so practically it means that we have a way of understanding how much data we can fit in a neural network, and there's examples in the papers. So the feature vectors is the neural population. That's what it means. And then we have a theory backed with geometric analysis, and we can, connect, find the manifold dimension, radius correlation, or the manifold capacity. They done this on the task level in neuroscience, and they're now trying to figure out how this translates to neural networks. This keynote on its own had a lot of articles and a lot of references, which I had to dig out. And it's one of my New Year's resolution to learn more about this this area. It looks very promising. And here are the references. So today we're finishing a little bit earlier. I'm going to give you some time back.